This video will be discussing the content checkpoint for the projectile motion unit. Before we get started on talking about these concepts, I want to take notice of this concept summary that I've put out. I have on here listed 4 main points that I think it's important to understand when you go into doing these problems. So the first thing is, there are some things in this unit that are always true. Number 1, horizontal velocity is constant. All right? The vertical acceleration for all objects is 10 meters per second downward regardless of mass. This is because gravity is the only force acting on the objects in projectile motion, and gravity has a tendency to accelerate the objects the same regardless of their mass. So all objects have a downward acceleration of 10 meters per second, which comes about due to gravity. Each second an object is moving, then its vertical velocity is changing by 10 meters per second. It's going down by 10 meters per second each second. All right, and as I said again, mass does not matter. Also for this entire unit, we are ignoring the effects of air resistance. We are assuming that the only force that is acting on the object is gravity. The second big point here is that 45 degrees creates the optimal angle for shooting a projectile from the ground. And then this is also, there's this double asterisk and bold statement here. It says, assuming that the initial speed of the projectile is the same. Okay, so what we're saying here is that if you have, say, a cannon that shoots at 40 meters per second, and you're trying to decide what direction to angle that cannon at to get the maximum range, 45 degrees is the best angle to put it at if you want to maximize range. This is because 45 degrees balances giving you a vertical velocity, which will give you larger hang time, and the horizontal velocity, which will help you move more quickly in the horizontal direction. Now, if you are changing the speeds at all for what's coming out of your projectile launcher, all of this goes out the window. All right, you cannot use this rule if you have different speeds coming out of the projectile launcher. And so 45 degrees is the optimal angle for a projectile, assuming that we have the same initial speed coming out of that launcher. The third big point here, initial y velocity, that v0 y, hang time, and maximum height are all directly related to one another. That means that if you are ranking them according to any of these 3 things, initial y velocity, hang time, or maximum height, sometimes I call that peak height, then all the rankings for all 3 of these are together because they all go hand in hand. All right, and then the last point here is that the horizontal distance traveled, that's delta x most oftentimes, is equal to the hang time multiplied by the horizontal velocity. So we have this thing where range equals hang time times vx. All right, and those are the only 2 things that range directly depends on. Using these ideas, you can hopefully better approach these concept problems, and that will help you throughout the entire test as long as you kind of have these different ideas. Okay, so on to the content checkpoint. It says here, because it's projectile motion, we're going to assume that there's no air resistance, and also that the acceleration due to gravity is 10 meters per second downward. Going on to the first question here, it says a ball is tossed into the air with an initial vertical velocity of 5 meters per second and an initial horizontal velocity of 15 meters per second. At its peak, what are its vertical velocity, horizontal velocity, and acceleration? So this calls into play actually a whole lot of different concepts, so I like this question because it brings in a few different concepts. First of all, at the peak, the vertical velocity is 0 at the peak of the motion. So anytime we have an object that is reaching its peak, it was going up, and then it reaches its peak, and then it's about to start heading back down. When it's at that peak, vertical velocity is 0. The second idea here is that horizontal velocity is constant. So if you have a 15 meter per second horizontal velocity initially, you always have a 15 meter per second horizontal velocity. And then here about the acceleration, acceleration is always 10 meters per second downward for the entire unit. So those are 3 general concepts that is good to know. Question number 2 says a penny is dropped off the top of a skyscraper. What will the speed be after falling for 5 seconds? All right, what will be its velocity? So each second, an object is accelerating 10 meters per second. So each second it gets 10 meters per second faster going in the downward direction if it's starting from rest. What that means is that after 5 seconds, we'll have a speed of 50 meters per second. That's 10 meters per second times 5 seconds. All right, so the speed will be 50 meters per second. Velocity is speed and direction, so velocity is going to be 50 meters per second downward. All right, because the velocity has to include that direction with it. Number 3, we have 2 archers. It says that they shoot arrows simultaneously. The first arrow has a mass of 0.2 kilograms. The second arrow has a mass of 0.4 kilograms. If the arrows reach the same maximum height in motion, which arrow strikes the ground first, and how do you know? The first thing here is I've given you some masses, but those masses are sort of to throw you off the trail. Mass does not matter in this unit. So it doesn't matter that one of the arrows is 0.2 kilograms and the other one is 0.4 kilograms, because mass does not affect the projectile motion of an object. All objects experience the same acceleration regardless of mass. The key to this question is actually that they say that they reach the same maximum height. If they reach the same maximum height, that means that they have the same hang time, or the same amount of time in the air. All right? Because hang time and initial y velocity and peak height or maximum height are all related to one another. So you know that they hit the ground at the same time because the peak height is directly related to the hang time of its motion. And so they have the same peak height, which means that they have the same time in the air. 4, 5, and 6 are all ranking tasks. Looking at this picture here, we have A, B, C, and D, which all shows cannon firing off of a cliff, all with the same initial speed. All right, but what's changing here is the direction between the different shots. And I say here, assume that A is going to come down a little bit ahead of the cliff. This is to avoid some confusion, where sometimes people think, well, what if A went up and then it came down, but it landed still on the edge of that cliff? What I'm saying is A is going to go up, and then it's going to come down, and then it's still going to fall all the way to the bottom of the cliff, to the ground. So it's going to land at the same height as all of the other shots. So number 4 says rank the projectiles from largest to smallest in order of how long they will be in the air. Well, how long they're in the air, in this case, and really in all cases, is directly related to the initial vertical velocity. A has the most vertical velocity, and then B, and then C, and then D. So for question 4, really we're looking at the amount of vertical velocity that they have. All right, and A has the highest vertical velocity, and then B is kind of partially upward. C starts out only horizontally, so it has no vertical velocity, and D is actually going down, so it's going to have the lowest amount of time in the air. For question 5, it says rank the projectiles from largest to smallest in order of horizontal velocity when they strike the ground. Okay, so to answer this question, you have to remember that horizontal velocity is constant. So their horizontal velocity when they strike the ground is going to be the same thing as their horizontal velocity when they were first launched. If you look at the different arrows here, C is the one that has the most horizontal velocity because it's pointed directly horizontally. B and D then have the second most, they're tied, and then A has the least because A actually has no horizontal velocity. Question 6 says rank the projectiles from largest to smallest in order of how far they will go, or how far they're going to travel horizontally, that is, in terms of their horizontal range. So if you look at these, hopefully it makes sense that B is going to go the furthest because it's going up into the air, and so it has a horizontal velocity that is more ideal, and then C after that, and then D, and then A. A is not going to go anywhere because A is just going to go up and come straight back down, so A won't go anywhere. We have just a couple more ranking tasks here. These are looking at a set of cannons that have the same horizontal velocity. They have the same Vx, 20 meters per second for Vx for all of them. The first question asks us to rank the projectiles from largest to smallest in order of their horizontal distance traveled or their range. To do this one, you have to remember that range depends on two things. range depends on horizontal velocity and hang time. They all have the same horizontal velocity, 20 meters per second for all of them, which means actually what we're looking at here is which ones have the most hang time. Hang time is dependent on vertical velocity. If you look at these, hopefully you can identify that E and F have the largest vertical velocity. That means that they have the largest hang time, and because all of them have the same Vx, the ones with the largest hang time will go the furthest. So E and F go the furthest, and then C and D are next, and then A and B go the least far, because those have the smallest vertical velocity and the smallest hang time. Question 8 asks us to rank the projectiles from largest to smallest in order of the maximum height that they achieve. For this one, we are looking also at the vertical velocity, because maximum height is directly related to initial vertical velocity. So it ends up actually being the same order. All right, E and F have the most initial vertical velocity, which means they reach the maximum height, then D and C, and then A and B. For question number 9, we need to create a set of motion graphs that are describing the motion of this bullet, and I set up here as a frame of reference up and right as being the positive direction, whereas down and left are negative. All right, and so these graphs are showing the projectile just after it launches, all right, and before it strikes the ground, all right, and then I'm assuming that the initial position is 0 for both axes. So for the vertical axis, you have to think about what's happening on the vertical axis in terms of position. It's going to be a curved line because it's accelerating on the vertical axis. The bullet is going to be going up at first, and then it's going to come back down. And so on the vertical axis, it just looks like that. It goes up, and then it comes back down. All right. For the vertical velocity versus time graph, again, we want to show something that's going up at first and then coming back down. And so we have a positive initial vertical velocity and then negative, and it returns to its original height. For the acceleration versus time in the vertical direction, acceleration in the vertical direction is always a constant. That should be a horizontal line. All right, and we know that this horizontal line falls at 10 meters per second downward, which I'll write as negative 10 meters per second per second. Next, we're going to do it for the horizontal direction. Now, something interesting here, I haven't done a lot of examples of this, but I said that right was the positive direction. This object is moving to the left, which means on the horizontal axis that the bullet is moving in the negative direction. Right is positive, left is negative, it's moving to the left. So all the horizontal movement is going to be in the negative direction. I just wanted you to see an example of that, so I'm going through and doing it this way. So in the position versus time graph, it starts out at 0, and it's moving with a constant negative velocity. It's moving with a constant velocity in the negative direction. And so what we end up with here is a straight line that comes down. It's a slanted line that comes down from the origin. For the velocity versus time, as I said, we have a constant negative velocity. So it's a line flat under the graph. And then for the acceleration on the x-axis, we have no acceleration, so it should be right at 0 for that. For the second section of this content checkpoint, I have a series of some problems that I'm going to go through. So I'll go through and explain each of those now. For this first one, it says that a daredevil is starting from rest and jumping off a cliff, and the daredevil is planning to fall straight down into a pool. It says she's traveling 80 meters per second when she strikes the water. How long did it take her to fall the first quarter of the distance to the pool? And so this question is a little bit strange, but what we're doing is, first we need to find out what the total distance the diver is going to fall in, and then we need to figure out how long it's going to take her to fall a quarter of that distance. So we end up with kind of two different situations here. First, I'm going to make a Vy versus t graph. There's no horizontal motion in this one, so I'm not really caring about the x direction. But a Vy versus t graph, it says that she starts from rest, and she's going in the negative direction. We know that this diver has 80 meters per second when she strikes the water. That 80 meters per second goes right here because that is her change in velocity. Then you have to think about how long that would take. Now, we know that change in velocity equals acceleration times time, all right? And in this unit, 10 is the acceleration. So change in velocity ends up equaling 10t, all right? And so t equals the change in velocity divided by 10, which means that the time that we have here is actually 8 seconds on that time axis. So to figure out how far this person is going to fall, we can say change in y, all right, the change in height, equals 1/2 times 8 times 80, which equals 320 meters. All right, that's the total distance that the person is going to fall. Now, it says how long does it take her to fall the first quarter of that distance. So what we want to do is figure out how long it takes her to fall 80 meters, because 80 is 1/4 of 320. We say 320 divided by 4, and we get 80 meters. All right, and then we're going to make a new situation where we've got Vy again here. And in this case, I want to see how long it takes her to fall 80 meters. All right, so in this case, then I know 80 is the area because that's the change in height. I don't know how long it's going to take, but I know the acceleration is 10, so I can call this t and 10t. So then I know 1/2 times t times 10t equals 80. That simplifies to 5t squared equals 80. And then we get t squared equals 16. And then t here, it has to be positive, so t equals 4 seconds. All right, so it takes this person 4 seconds to reach 1/4 of the total distance. Some people look at this and they think it's kind of funny because it took her 8 seconds to fall the entire distance. And so some people are like, wait, it takes half the time to fall 1/4 of the distance. How does that make any sense? But remember that this woman is accelerating as she's going down. So it actually does make sense that it should take half of the time for her to fall 1/4 of the distance because she's speeding up as she goes down. So as we get later and later, she's falling faster and faster and covering more distance. So after 4 seconds, she has covered 1/4 of the total distance to the pool. Question number 2, we have a plane that is flying horizontally with a velocity of 100 meters per second. And then I say it drops a package, which lands on the ground 4,500 meters below. And I want to know the horizontal distance that it covers. So for this one, we make again a Vy versus t graph. The Vy versus t graph is the most common thing that we're going to make in this unit. For this one, it's dropped out of a plane, so initially it's not going up or down, it's just going horizontally. So again, we start with this one where it starts with a y velocity of 0. We know that this box fell a distance of 4,500 meters to the ground, so we know the area of that triangle is 4,500. This is another case where we don't know time and we don't know change in velocity, so I call it t and 10t. And then I know 1/2 times t times 10t equals 4,500. All right, so then I know 5t squared equals 4,500. And then t squared is going to equal 900. And then what we get here is that t equals 30. So we find that time is 30 seconds. Now to figure out how far it's going to go horizontally, I look at the horizontal velocity versus time graph. That is my Vx versus t graph. It's a constant positive velocity. I want to find the area to figure out how far it goes. I know that it's falling for 30 seconds. I know that it's traveling with a horizontal velocity of 100 meters per second because that's what it had said originally. So we take 100 times 30. delta x here equals 100 times 30. And what we get there is that that equals 3,000 meters. So 3,000 meters is the horizontal distance that the package covers, which is actually quite a long distance, but remember that it fell 4,500 meters, so we're talking pretty big distances here. On the last problem here, we've got an archer that's standing on top of a castle wall. The archer is going to aim and fire an arrow 30 degrees below the horizontal with an overall velocity of 40 meters per second, and it strikes a soldier below who's standing on the ground. It strikes 3 seconds later. I ask, how far below the archer vertically was the soldier standing, and what was the horizontal range of the arrow? So for this one, first, anytime that I give you an angle in the problem, we've got this happening at an angle. What we need here is to break down the angle, break down the velocity into parts. I know it was going 40 meters per second, and I know that this was happening at an angle of 30 degrees below the horizontal. Other things I know is that if we use the trigonometry, then we get v naught x, which is just really the horizontal velocity all the time, is 34.6 meters per second, and v naught y, the original y velocity here, equals 20 meters per second. All right, but it's really downward, okay? It's 20 meters per second downward. And that's important because now we're going to make our Vy versus t graph. And in this one, we start off with a little negative component there to our velocity because velocity starts off negative in the y direction. It's 20 degrees because this person is firing the arrow below the horizontal. They're firing it down and forward. So this makes that situation where we have a rectangle and a triangle. We know that the initial y velocity here is negative 20 or 20 below the horizontal. We also know that it takes 3 seconds to hit the soldier. In that time, then, this change in velocity, which happens between here and here, we know that this change in velocity equals 30 because it's 10t. And so we have a triangle here with side lengths 30 and 3, and a rectangle with side lengths 3 and 20. And so what we can do to find the distance is we say that delta y here equals 1/2 times base times height for the triangle. That's 1/2 times 30 times 3. And then we know this is plus the area of the rectangle, which is 3 times 20. All right, and you add those together and you should get 105 meters. All right, that is your change in height. Okay, so that is how far below the archer that soldier is standing. To find the change in horizontal position, we need to make a Vx versus t graph. So I make a Vx here versus t graph. Constant velocity in the x direction. I know it's going for 3 seconds. I also, from my triangle that I did back at the beginning, I know that the x velocity is 34.6. I want to find that area there because I know then that delta x equals 3 times 34.6, which equals 103.8 meters. All right, so that is how far away horizontally the archer is standing, or the soldier is standing from the archer. These problems give you a pretty good indication of generally what to expect, but make sure that you go through and look through all the practice worksheets that we did because there are a lot of different ways that these projectile motion problems can come at you. You probably want to watch that other video that I put out on projectile motion, which summarizes some key concepts there and goes through some different example problems. And just also there were some worksheets that we did in class that there were not keys for, but look through those, Make sure that they all make sense, and if you have any questions, as always, make sure you come in and ask.